Hello everyone, welcome to the vCIES 2020 workshop for the Network Data Analysis and Visualization. My name is Byung-Gyu Kong. For the next couple of hours, we will explore the network data analysis and visualization from theory to practice. I hope this time will be fruitful for everyone who registered for this workshop program. Before we jump into the session, let me introduce myself just briefly. My name is Byung-Gyu Kong, a PhD candidate of Education Policy and Evaluation Program at Arizona State University. My research interest is knowledge and concept mapping of the educational field. For this, I mostly use network analysis methods using citation network of documents. Also, I recently explored text mining skills to the topic modeling with machine learning technique. My current research focuses on mapping the studies of artificial intelligence and education studies to see the interaction between the two fields with growing popularity of AI technology. By measuring and detecting a pattern of interaction between the two fields, I try to envision the future of education study under the influence of the AI technology. I'm also looking at patent data to map out the trend of education technology, and also looking at psychometric studies in education testing with a similar motivation. So, in overall, my research agenda is pretty much defined by the network analysis method. This course targets Bayesian level audiences who have not much heard of the network theory and analysis before. Accordingly, this lecture aims to make participants to understand the basics of network theories with their fundamentals and mathematical concepts. And secondly, understand how the data can be archived, structured, and analyzed for the network analysis using RStudio and Gephi. And finally, understand how the network data can be visualized using RStudio and Gephi. This course does not cover mathematics of the network theories, does not using highly abstract mathematical formula of the network theories. But I will try to let you uptake some of the key features of the network mathematics and get a sense of mathematical concept in this lecture. Also, I will guide you to create the real network object using the data analysis softwares so that you can have a chance to experience how the network theories are materialized in the software tools. This lecture consists of two sessions. In the first session, we'll concentrate on concepts and theories. In this part, I'll briefly introduce the basic definition, history, and examples of network analysis, and then move on to the fundamentals and mathematical concepts of the network theories. Through this part of the lecture, we'll learn what is the network, how it was conceived, and what are the main features of the network. In the second session, we'll get our hand dirty by running the real analysis using iGraph and Gephi software. You'll get a chance to run the network analysis using a real-world example, and how the theories and concepts you learn are calculated and visualized through the softwares. The entire session will take approximately 2 hours. Then, let me start with the concepts and theories. I will start by introducing definition, history, and examples of the network analysis. Okay, then what is the network? It seems very complicated and difficult to define a network. At first, once you see the large size of complex global network, as you can see the example here. Even this example is a very small part of the global network. But let's try to zoom up only this part here on the left side. It is embarrassingly simple, and if you felt in that way, you're right. The basic element of the network is a pair of dots with a single connecting line. Not more than that. Whatever complex the network is, they can be all broken down into this small element, consisting of one pair of dots with a single connecting line. So you don't need to feel overwhelmed by the complex large-sized network. That is the reason why Newman defined network as a collection of points joined together by lines. Usually the dot is called node or vertex, and the line is called line or edge. I recommend you to get used to both terms, as they are widely used and not strictly differentiated. You should keep in mind that memorizing the right terms is the first thing you should do to start this long journey. So, before moving to the next page, please repeat for yourself that dots are called node or vertex, and lines are called line or edge. There are many different kinds of network exist in the world, and I will briefly mention about representative network examples here. Most symbolic example is our internet. Internet is a collection of small connections between computers and routers through cables and wireless router connections. Power grid is also has a very similar structure. In social network, we can assume that there is a friendship network wherein each person is connected to each other through feelings of affinity. In academia, we're supposed to refer to each other, and thanks to this practice, there is a large web of citation network. The citation network analysis is one of the most frequently used methods in the comparative and international education studies, as there is a lot of common research interest in diffusion, borrowing, and transfer studies of education policy. I'll briefly introduce some of the examples at the end of the lecture. Biology is also one of the largest fields leading the research in network analysis, as our body, brain, and ecosystem is composed of complex network. There is a line of intellectual history in the developmental path of the network analysis. It was largely recognized that the network theory started from the graph theory, and the famous example is Königsberg bridge problem. Euler proved that there is no single path that can cross each bridge only one time to cross all 7 bridges, using graph abstraction method. Then later on, from 1960s to 1990s, social science was one of the most influential fields developing network analysis theories. Morano's sociogram was the pioneering research of the social network analysis. This research created friendship network based on a simple question to ask to each student: who wants to be sitting next to whom? The results clearly mapped out how the gender divide grows as students grow up from 1st to 6th grade. Even though the network analysis has been nurtured and popularized by the social scientists for a long while, the recent development shows it is moving toward more general theory of network science as the available data increases and big data analytics looms over. For instance, thanks to the development of internet, the researchers do not need to do social survey to ask the level of affinity between friends, but rather collect direct interaction data through a social network in online or personal device measuring physical distance between students. And that way, the researchers started creating hard data. This new movement synthesizes concept and mathematics-based graph theory with empirical case-based social network analysis. The example picture here is from the Grant Gin's Twitter network. Grant Gin is one of the founding fathers of network software Gephi. As you can see from this picture, this clearly shows the massive size of social network and its details with visualization techniques, differentiating each vertex and edges with size, color, and distance. The network studies usually but not exclusively aim to understand the pattern of connection and interaction. With structured features of the network researchers aim to explain behavior and phenomenon. But such abstraction of the real-world phenomenon comes at a cost of losing a lot of information. Just imagine that complex interpersonal relationship is reduced into a single line counted as one. Researchers would refer to each other with multiple reasons. Some may refer to others to criticize, recognize, or appeal to authority. But in the network analysis, such complexity is largely ignored, and they are simply represented as vertices and edges. However, still such a high level of abstraction is useful to understand the real-world phenomenon, because it allows large-scale and efficient calculation of the network structure. I'd like to talk more detail about the networks of various occasions, because each network shares common features with minor differences. Once you can understand the universal feature of the network, you can predict the nature of each different network. First example is an internet, which hardwires computers through the optic fiber. This picture indicates the internet network at the global scale. At the core of the network, there are high-performing routers sending signals long distance. They are mostly possessed by the large telecommunication companies. At the semi-core, there are intermediary providers and resellers. And the periphery is filled with end users. In this way, the broad mapping of the network instantly provides a glimpse of the power dynamics of the network through density, color, and size. The social network represents connection, interaction, and relationship between people. The vertex means person, group, family, class, organization, or even nations. In the social network, unlike other physical networks such as power grid or neural net, edge mostly indicates invisible and abstract connection between people, such as contact, affinity, or co-membership. The social network has usually been a small-sized network, centering around each key person in a small group or organization, which is called ego network. But thanks to the recent development of big data and data mining, the size of social network has been dramatically enlarged, and it enabled researchers to have more bird's-eye view of social network phenomena. The given picture shows the Twitter network. In this picture, the core entails person with more power, reputation, or better access to the social capital. The information network has been one of the oldest subfields of network science, independently developed theory and concept for a long while, taking a large portion of network studies in social science these days. It usually composes a network out of citation network of each document. Citation practice is a common role in academic, legal, and patent writing, revealing how the document is created and influenced by the other existing papers. In citation network, the vertex can be document, journal, subject area, author, institution, and even nations. The edges can be citation, membership of the articles and authors. Also, citation network studies emphasizes co-citation or bibliographic coupling, which represent the share of the same reference in its citation list. So, in this co-citation or bibliographic coupling, edges between two vertices means they share the common reference in their reference list. In these days, with a big data and text mining techniques, co-occurrence of certain keywords is also a key to explore network structure of the documents. This picture is from my research exploring citation network of the education and AI papers. The core of the network includes the most cited papers or authors, and this means they have higher academic reputation and performance. The citation network analysis is widely used to identify key scientific research investment, as the network reveals what kind of research topic is the most popular in a certain field. This citation network analysis technique is used to identify vaccine development of the COVID-19, to identify the state of the art of the vaccine research, helping to set the next research agenda. The last network example is the biological network. Biological network is also one of key areas of network science. In particular, neural network is our brain has been a source of inspiration for other physical and electrical network systems, with credit for computer and chips. The special feature of the neural network is that it is three-dimensional network, not a two-dimensional unlike most of the other networks. Also, neural network is a dynamic network system, changing its shape and pattern according to the input and output frequency and intensity. Thus, it is one of the most challenging network objects for many of the network scientists, and more new discoveries are expected. So now you learned what is a network and how many different kinds of network structure is commonly explained and represented by universal elements of vertices and edges. Then let's jump into the fundamentals and mathematical concepts of network theories. Understanding the structure of the network data is the very key to calculate network features using software tools. As a network analysis softwares only allows certain format of data structure. The most basic data structure for the network analysis is a node list. Node list is a vector of vertices in the network. Let's assume that there is a network with 6 vertices. Then as you can see in this example, the node list will be a single column or vector of the nodes. It is pretty much simple. The major role of node list is giving attribute to each vertices almost limitlessly. For instance, each node in this node list can have gender, age, and grade as its node attributes. Such information in the node attributes take a critical role in visualizing the network, giving different color and size to each vertices depending on the node attributes. But as we all know, network is not complete only with the dots. We need to represent the connecting lines between the dots. Edge list is a vector composed of a pair of vertices having connection to each others. In this example, vertex 1 has connecting line with vertex 2 and vertex 4. These connections are presented as pair of numbers like 1 and 2 and 1 and 4 in the edge list. The edge list is the very key for the network analysis, as node list is redundant when we have an edge list. It is because the edge list gives information of node list, but node list does not give information about edges. Edge list also has edge attribute information. It is mostly about edge weights given by frequency or intensity of the interaction between vertices. In this example, I just assigned edge weight with a standardized score from 0 to 1. So each edge should have a different edge weight here. The last but the most important data structure you should learn is the adjacency matrix. Once you can understand the adjacency matrix, it is much easier to comprehend many complex mathematical representations of the network analysis. It is still pretty much simple. The adjacency matrix presents 1 when there is an edge between the two vertices, or 0 when there is no connection. If there is edge weights, each number in the matrix element will represent edge weights. As you can see in this example, the adjacency matrix includes nodes and edge list information in one place. So each of the row and column names represent node list, and each of the numbers like 1 and 0 represent the edge list. To build up your data for the network visualization, you need to structure your data set to represent edge list or adjacency matrix. To create a network showing node and edge attributes, you need to build up your data set to include node and edge list. Later on at the session 2, I will show you how the raw data structured as node list and edge list ready for analysis and visualization through iGraph and Gephi software. But one thing I want you to keep in mind is that whatever data you have, once you can convert them into edge list or adjacency matrix, you can create your own network data and graph. There are many different types of network according to their key features. So from this slide, I will introduce some of the essential key features of the network. Firstly, the network is divided into two groups of undirected or directed network according to its edge types. In the undirected network, the pair of vertices in its edge list is not ordered. In this example, the pair of vertices I and j is not ordered. That means I and j is equal to j and I, which is because the order doesn't matter. But in the directed network, the pair of vertices is ordered. Thus, I and j is not the same as j and I. Then let's see how the undirected or directed network is represented through the edge list and adjacency matrix. First, I recommend you to practice writing edge list and adjacency matrix here for yourself. Just pause this video for a few minutes and try to write down the answers as you learn how to do it previously. Then I will show you the answers. Okay, now let's check up the answers. First, let's look at the edge list. The answers should be like this. Did you recognize a difference between the directed and undirected network? In the edge list of the undirected network, the pair of vertices does not indicate any directionality. For instance, 1 and 2 does not entail that information flows from 1 to 2. It just indicates that there is a connection between the two. But in the edge list of the directed network, the pair of vertices entail a direction. Thus, 1 and 2 in the edge list means that the information flows from 1 to 2. Then let's check out the answers for the adjacency matrix. For the undirected network, the adjacency matrix is symmetric. But in the directed network, the adjacency matrix is asymmetric. That is because a pair of vertices represents directionality. So for example, the 1 and 2 and 2 and 1 in the undirected network, they're the same. But in the directed network, the pair of vertices of 1 and 2 and 2 and 1, they show different numbers. The second key features of the network is edge weight. The network has been introduced so far in this lecture was all unweighted one. In the unweighted network, edge only represents information of whether there is a link or not. But in the weighted network, edge represents strength or intensity of the connection. The thickness of the edge shows the strength of the tie. Then let's see how the unweighted or weighted network is represented through the edge list and adjacency matrix. As we did before, just pause this video for a few minutes and try to write down the answers for the weighted network below. Then I will show you the answers later on. Now let's check up the answers. The edge list of the weighted network has an extra column for the edge attributes. This is the edge weight and shows how strongly each vertices are connected. In the adjacency matrix, the previous mark of 1 in the unweighted network is replaced with the edge weights. For example, in the edge list of 2 and 1, the previous mark of 1 was replaced by the edge weight of 2. Bipartite network means the network having two different types of vertices. For instance, in the example in this slide, vertices denoted as I indicates a person, while J means event. In the bipartite network, vertices in the same category does not share direct edges between them, unlike the non-bipartite network. This is a very special kind of network but widely used more than we thought. Then let's write edge list and adjacency matrix of the bipartite network. Please pause the video for a while and try to find an answer. Okay, then let's check up the answers. Making up the edge list should not be difficult as it is not much different from the previous undirected networks. But there is a huge difference in the representation of the adjacency matrix. You would see the rectangular shape of adjacency matrix having only events vertices I1, I2 as its row names, while only person vertices J1, J2, J3 as its column names. This is called incident matrix. As we learned, bipartite network does not allow to create edges between the same kind of vertices. But there is a way to transform this network to represent co-membership or proximity network, marking a direct edges between the same kind of vertices. In this example bipartite network, each vertices on the left noticed as J is people, and on the right noticed as I means events. We can create event network here based on the shared participants. This may give us an information on the characteristics of each event based on its composition of participants. Also, we can create social network of the people based on their event participation, like here. And the social network, people are connected based on their shared event experiences, which gives a glimpse of their personal interest. And this reason, bipartite network is very important for the network analysis. Centrality means the strength or power of the nodes inside of the network. The centrality means has been considered to be the most important index we can create out of the network data. Thus, from this slide, we will explore various measures of centrality. The first centrality measure is a degree. Degree is the number of edges linked to each vertex. In this example network, vertex 1 has 2 degrees as it has 2 edges. For a directed network, there is only one type of degree. But for a directed network, there are 2 types of degrees, in degree and out degree. As you can see here, in degree means the edges heading to the given vertex, while out degree means the edge coming out of the given vertex. The degree centrality is the simplest measure of centrality, summing up all the degrees each vertex has. In this example network, node attribute is the degree centrality, and it simply sums up all edges each vertex has. And according to the degree centrality, the size of the vertices is decided. The bigger vertices has the bigger score of degree centrality. One of the variations of the degree centrality is an eigenvector centrality. The basic concept is this: vertices having neighbors with more degree centrality have more power than vertices having neighbors with less degree centrality. This concept totally makes sense once you consider the fact that having too many friends who don't have much power to give critical information does not help you out. Rather, you'd better know a small number of neighbors having large information resources with better social capital. According to this definition, eigenvector centrality sums the scores of its neighbors' degree centrality. Let me give you an example here. The vertex 1 has 2 neighbors of vertex 2 and 4. Vertex 2 and 4 has 3 and 5 of degree centrality for each. Thus, the eigenvector centrality of vertex 1 is 8, the sum of 5 and 3 and 5. According to this calculation, you will find that vertex 3 and vertex 5 having the same level of degree centrality of 2 shows different level of eigenvector centrality of 8 and 7 for each. This means that vertex 3 has more connection with the powerful vertices than vertex 5. Then, the next centrality measure to introduce is betweenness centrality. The betweenness centrality of a vertex is counted by the number of shortest paths between any pair of vertices passing through the vertex. Let's just assume that, as in the example picture here, 2 clusters of network is connected only through the yellow vertex. If that is the case, although the degree centrality of the yellow one is only 2, its betweenness centrality must be incredibly huge. Then, why the betweenness centrality has such an importance? Just imagine that we delete the yellow vertex here. Then, we will lose a large number of connections because That was the only way the two clusters are connected to each other. So, vertices with high betweenness centrality are gatekeepers, controlling the flow of information and influence passing between others. There are some key measures representing network structure we should know. From this slide, I will show you some of the measures informing the overall network structure. The first one to introduce here is the network density. The network density is simply calculated by the number of edges divided by the total number of possible edges. The possible edges mean that the maximum number of edges physically and mathematically allowed to the given number of vertices. Through a simple example, I will elaborate it further. Look at the network here at the left side of the slide. There are 5 vertices and 5 edges, but it does not represent the maximum number of edges allowed to this network. As we can see from the below network, the maximum number of edges we can draw is 10. Then the network density of this network would be 0.5. Assortativity is also one of the measures showing the network structure. Assortativity is defined as the tendency of vertices to connect to others that are like them in some way. We can see many of the real-world examples of the assortative mixing, such as friendship network, clustering together with the same gender, age, and income, and also faculty co-authorships grouping together with the same field and nationality. It is calculated by subtracting a fraction of edges connecting between vertices of the same type in a random graph from a fraction of edges connecting between vertices of the same type in the graph. The random graph means the artificial graph having edge connections by chance with the given number of vertices. Assortativity score ranges from -1 to 1, and once we get the minus score, it means that there is a reverse tendency of vertices connecting to others having different characteristics. Such dissortativity prevails in the neural net and food web in biology. Community detection is also one of the key analytic techniques the network data provides. By detecting communities, we can discover new patterns and substructure of the network. Newman defines community detection as it is the problem of finding the natural divisions of a network into groups of vertices, such that there are many edges within groups and few edges between groups. Then how can we detect such community structure? We can use the modularity score and iterate scoring until we reach an optimum level. The optimum level means the moment when we can get higher modularity score than a random graph. Let me elaborate this iterative process further here. The Leuven method is one of the variations of the modularity optimization technique widely used in iGraph and Gephi. We have a network here, and then each of the iterative calculation, we will produce modularity scores and continue this iteration until we reach a plateau. As you can see from this picture, every iteration it tries adding other vertices into the cluster and calculate the modularity score. The score increased pretty much at the initial phase, but it reaches to the flat moment later on. Then as a final product, you would see this clustered network graph. I will show you how it really walks through the YouTube video clip. This is the YouTube video clip uploaded by Kate Jolie, and it looks really great, and it shows how it really walks for the community detection of network analysis. I will play this video. As you can see at the initial moment, the modularity score increases a lot. On the left side, it shows how it really works. It tries to include more vertices into some clusters and it changes really fast. The color is changing. It means that more vertices are included in the cluster. But once it reaches a certain moment after some of the iteration, it doesn't increase pretty much. It's almost the same after some of the iteration. It's not productive anymore. Once it continues like this long time, the loop-end method turns into a simple network of cluster. As you can see the left, it's kind of abstraction of the complex network into a small number of clusters. So it's kind of simplification of the network. So each of the vertices represent the communities, clusters identified so far, and it continues iteration more time with this cluster network. That's a key feature of the loop-end method. So once it increases modularity as much as it can, after the second phase, it stops. So this is the end of the first session for the theory and concepts of the network analysis. I recommend you to repeat this video 1 or 2 more times before we jump into the practice session. As I noticed before, this lecture is for the beginners of the network analysis. Thus, I skipped many more of network analysis measures for this lecture. I hope I will get more chance to develop this lecture for the intermediate and advanced level audiences in the near future.